Good day everyone, I am Hazel Ann Corpus, and today my report is all about the section 3.2 linear combinations of measurements. Uncertainties change when performing arithmetic operations on measurements. Adding constants, multiplying by constants, or combining measurements affects uncertainty. Since measurements are random variables, their uncertainties or standard deviations follow statistical rules for linear combinations of random variables. These principles help compute uncertainties in calculated values. We all know when we measure something, it's never 100% exact. There's always a small error or uncertainty. If we add, subtract, or multiply these measurements, the uncertainties also change. So we need a way to know how big the uncertainty is after we do those operations. So this section helps us correctly calculate the uncertainty when we combine measurements so that our final results are reliable and accurate. These are the equations used to compute the uncertainties in linear combinations of independent measurements. Okay, so let's begin to the example 3.4. The radius of a circle is measured to be 3.0 plus or minus 0.1. Estimate the circumference and find the uncertainty in the estimate. Solution. First is we need to identify the given. So the radius is equals to 3.0 centimeter. The uncertainty in radius is equals to 0.1, and we all know that the circumference of a circle is equals to 2 pi r. In order to find the circumference of the circle based on the radius given, we just need to substitute the value of r, which is 3.0 centimeter in the equation. And makukuha natin yung sagot na 18.85 centimeter. Next, to find the uncertainty in the estimate, we need to use the equation 3.3. And we just need to substitute the given para makuha yung uncertainty na 0.63 centimeter. So we conclude that the circumference is 18.85 plus or minus 0.63 centimeter. Next is the example 3.5. An item is formed by placing two components end to end. The lengths of the components are measured independently by a process that yields a random measurement with uncertainty of 0.1 centimeter. The length of the item is estimated by adding the two measured lengths. Assume that the measurements are 4.10 centimeter and 3.70 centimeter. Estimate the length of the item and find the uncertainty in the estimate. Solution. We need to identify the given first. The length of the first component is equals to 4.10 centimeter. The length of the second component is 3.70 centimeter. And the uncertainty of the first and second component is equals to 0.1 centimeter. To find the estimated length, we need to add the length of the first component and the length of the second component. And the answer is 70.80 centimeter. And next, to find the uncertainty, we need to use the equation 3.4. And by substituting the given in the equation, we get 0.14 centimeter as the uncertainty. So we conclude that the estimated length is 70.80 plus or minus 0.14 centimeter. Next is the repeated measurements. A key method to reduce uncertainty is averaging multiple independent measurements. These measurements form a random sample and their average is the sample mean. So repeated measurements helps in order for us to get a better results and more accurate results because we need to measure the same thing several times independently. And each time we get a slightly different value because of random errors. Then we find the average or the mean of all those measurements. So in short, taking several measurements and averaging them reduces the uncertainty in your final answer, which gives us a more reliable estimate of the true value. Let's proceed to the example 3.9. The mass of a rock is measured 5 times on a scale whose uncertainty is unknown. The 5 measurements in grams are 21.10, 21.05, 20.98, 21.12, and 21.05. Estimate the mass of the rock and find the uncertainty in the estimate. Solution. So we need to identify the given. We let x bar as the average of the 5 measurements, and s is the sample standard deviation. The 5 measurements are 21.10, 21.05, 20.98, 21.12, and 21.05. To find the average of the 5 measurement, we need to add the 5 measurement and we divide it by 5. And the answer is 21.06 grams. And that is the estimated mass of the rock. To find the sample standard deviation, we just need to use the equation in the previous topic and substitute the given. And we get 0.0543 grams. So, pwede na nating mahanap yung uncertainty in the estimate using the equation 3.6. Dahil nakuha na natin ang value ng S and N, we just need to substitute it. And we get 0.02 grams. Therefore, the mass of the rock is 21.06 plus or minus 0.02 grams. Next is the repeated measurements with differing uncertainties. Sometimes repeated measurements may have differing uncertainties. This can happen, for example, when the measurements are made with different instruments. It turns out that the best way to combine the measurements in this case is with a weighted average rather than with the sample mean. This means that some measurements are more reliable and others are less reliable. So instead of just averaging them equally, we use a weighted average. That means we give more weight to the measurement we trust more and less weight to the ones with more uncertainty, which gives us a better and more accurate result. Example 3.11. An engineer measures the period of a pendulum in seconds to be 2.0 plus or minus 0.2 seconds. Another independent measurement is made with a more precise clock, and the result is 2.2 plus or minus 0.1 seconds. The average of these two measurements is 0.1 seconds. Find the uncertainty in this quantity. Solution. We need to identify the given first. We let x as measurement 1, y is equals to measurement 2, x bar is the average, standard deviation of x is the uncertainty of x, and standard deviation of y is the uncertainty of y. And x is equals to 2.0, the uncertainty of x is 0.2, y is equals to 2.2, and the uncertainty of y is 0.1. The average is equals to 1/2 x plus 1/2 y, which is equals to 2.1 seconds. Next is we can now find the uncertainty in the average. By using the equation 3.4 and substituting the given, we get 0.11 seconds. Next is the example 3.12. In example 3.11, another engineer suggests that since y is a more precise measurement than x, a weighted average in which y is weighted more heavily than x might be more precise than the unweighted average. Specifically, the engineer suggests that by choosing an appropriate constant c between 0 and 1, the weighted average c times x plus the quantity of 1 minus c times y might have a smaller uncertainty than the unweighted average 1/2 times x plus 1/2 times y considered in example 3.11. Express the uncertainty in the weighted average c times x plus the quantity of 1 minus c times y in terms of c and find the value of c that minimizes the uncertainty. Solution. First is we need to identify the given. We let standard deviation of x is equals to the uncertainty in x, standard deviation in y is equals to the uncertainty in y, and t is equals to the weighted average. The uncertainty in x is equals to 0.2 seconds. The uncertainty in y is equals to 0.1 seconds. And the weighted average is equals to c times x plus quantity of 1 minus c times y. And we need to find the uncertainty of weighted average in terms of c, the value of c that minimizes the uncertainty, and the minimum uncertainty. To find the uncertainty in the weighted average, we need to use the equation 3.4 and substitute given. And we get the square root of 0.05 times c squared minus 0.02 times c plus 0.01. By taking the square root, we get the uncertainty squared is equal to 0.05 c squared minus 0.02 c plus 0.01. To find the value of c that minimizes the uncertainty, we need to take the derivative of uncertainty squared is equals to 0.5 c squared minus 0.02 c plus 0.01 with respect to c. And we get 0.10 c minus 0.02. And we can now find the value of c, and it is equals to 0.02. Now we can find the most precise weighted average by substituting the value of c. And we get 0.02x plus 0.08y. And by substituting the value of x and y from the example 3.11, we get 2.16 seconds as the most precise weighted average. After finding the most precise weighted average, we can now find the uncertainty in the estimate. By using the equation 3.4 and substitute the given tulad ng ginawa kanina, we can get 0.09 seconds. As we can see, 0.09 is less than the uncertainty of 0.11 found for the unweighted average used in 3.11. So this is the summary. If x and y are independent measurements of the same quantity with uncertainties of x and y respectively, then the weighted average of x and y with the smallest uncertainty is given by the c best times x plus the quantity of 1 minus c best times y, where c best is equals to the uncertainty of y squared all over the uncertainty of x squared plus the uncertainty of y squared. And 1 minus c best is equals to the uncertainty of x squared all over the uncertainty of x squared plus uncertainty of y squared. Next is the linear combinations of dependent measurements. When measurements are not independent, their uncertainties can be combined normally, and we can use this method when measurements may be dependent to avoid underestimating uncertainty, which gives us a safe upper bound. So this is the formula. If x sub 1 up to x sub n are measurements and c sub 1 up to c sub n are constant, then the uncertainty in linear combination c sub 1 times x sub 1 plus c sub 2 times x sub 2 up to c sub n times x sub n is less than or equal to the sum of the absolute values of the constant c sub 1 times the uncertainty of x sub 1 up to the absolute values of the constant c sub n times the uncertainties of x sub n. So let's proceed to the example 3.13. A surveyor is measuring the perimeter of a rectangular lot. He measures two adjacent sides to be 50.11 plus or minus 0.05 meter and 75.21 plus or minus 0.08 meter. These measurements are not necessarily independent. Find a conservative estimate of the uncertainty in perimeter of the lot. First is we need to identify the given. We let x sub 1 as the measurement 1, x sub 2 measurement 2, and the standard deviation of x sub 1 is the uncertainty in measurement 1 and the standard deviation on x sub 2 as the uncertainty in measurement 2. And x sub 1 is equals to 50.11 and the uncertainty in x sub 1 is equals to 0.05, x sub 2 is equals to 75.21 and the uncertainty in x sub 2 is 0.08. And we can write the perimeter as 2 times x sub 1 plus 2 times x sub 2. In finding a conservative estimate of the uncertainty in the parameter of the lot, we can use the equation 3.8 and substitute the given, and we get 0.26 meter.